Bueno, muy bien. Bienvenidos y bienvenidas a este nuevo coloquio de Cima de Cabo. En esta oportunidad tenemos el gusto de tener a Sarah-Jeanne Roger, que es una oceanógrafa y especialista en la degradación de plástico en el océano.
Hola. Muy bien. Bienvenidos.
Disculpen.
Bienvenidas.
Se me inició la transmisión. Sara es una investigadora en la Universidad de Hawái, en la isla de Oahu, y también colabora con el Instituto Scripps en la Universidad de California, San Diego, y en este momento estudia distintos polímeros, como por ejemplo microfibras sintéticas y su tiempo de degradación en el océano. También investiga distintas fuentes y sumideros que vinculan al plástico con el océano, como por ejemplo la industria de la pesca, y el balance total, su lugar en el balance total de plástico en el océano, y hoy nos va a hablar de parte de su trabajo. Así que gracias, Sara, y te dejo el escenario.
Muchas gracias. Infelizmente voy a hablar en inglés porque mi castellano es un poco complicado, así que voy a empezar en inglés. Si hay cualquier pregunta, no hay problema, puedes preguntarme a cualquier momento. So empezamos. So today I'm going to introduce my topic that I did during my postdoc, and it's mostly looking into plastic that is in the environment. So as most of you know, there's a very large amount of plastic that gets discarded every year in the environment, in the ocean, in landfills. And if we look at this work here from Gaillard et al. In 2017, they try to make prediction to look at the amount of plastic discarded up to 2050. And as you can see here, it will keep on increasing if the plastic waste management issues are still the same in the next 30 years. And if we continue growing, if the population keeps on increasing and consuming plastic, which is very sad because today the issue is gigantic. And if we look at this, we can see that it will more than double for 2050. This is the type of scenery, unfortunately, that we see in Hawaii. This is the island of Oahu, where I live. It's not very far from where I live, actually. You go there at the beach, James Campbell National Wildlife Refuge, and very often you see this amount of plastic. And about 95% of this plastic is actually coming from outside of the Hawaiian island. So it's mostly hard plastic. It comes mostly from Asia because of the geographical position of the Hawaiian Islands. And these are the plastic that will remain in the ocean for a very, very long time and start degrading and ends up at this refuge on Oahu. Half of this debris usually comes from the fishing industry. So it's really debris that's been discarded from the ocean to the ocean, and it's really meant to last for a very long amount of time. So the statistics are that every minute, one garbage truck of plastic is dumped into our oceans. This is a lot. It's about 8 million metric tons of plastic every year. And this number keeps on increasing, as shown in the first graph. One of the most popular questions amongst the plastic scientific community is actually the question about the missing plastic. So we take this one garbage truck of plastic that gets discarded into the ocean every minute, and then if us scientists are trying to look into the sinks once it reaches the ocean, we find only 1% of this plastic that gets discarded. So 99% of the plastic is actually missing. Of course, with the technology that we have today, the easier way to quantify plastic in the ocean is to use a manta trawl to scoop the surface of the ocean and to look at the concentrations. And this is mostly for floating plastic because the plastic with a density higher than seawater will sink. So all of the plastic that can be found in other sinks, we started quantifying these sinks better, but the amount is very minimal. So we use for many, many years this 99% of plastic is missing, and we are trying to answer the question, but this 99% with more research keeps on decreasing. But still, I would say we are still in the area of 90% of the plastic is missing. So this is a really big question. And where I do work also with the ocean cleanup with Laurent Le Breton, and Laurent is doing some modeling to help understanding where the plastic is going once it reaches the ocean. So there are a few options, and I'm not going to explain all of them, but at least I wanted to name them. So once plastic actually reaches the ocean, if the density of the plastic is lower than seawater, it will float. So it goes at the ocean surface. Then if the density is higher than seawater, it will sink at the bottom of the ocean in the sediments. Then the ingestions by marine life, so marine life will by mistake ingest plastic, and hence their stomach is also a sink. You have the marine snow. Then you have also the nano and pico particles, because once plastic starts degrading and fragmenting in the ocean, it can go to nano and pico sizes, which are very difficult to sample. So a lot of the plastic is actually invisible to the naked eyes and very hard to sample from a technical point of view. So a lot of this fraction might be invisible to the naked eyes. Then in the water column, so you have your plastic that basically floats. This is polyethylene, polypropylene, for example. But once you have the biology starting living on it, not necessarily degrading it, but using plastic as a substrate, the density of the plastic will change. So the plastic can encounter itself in the water column and just change the buoyancy of the particle itself. And this is also very hard to quantify. And then you have the rebeaching event. So as shown in the picture from Hawaii, a lot of the plastic that we have on our beaches comes from the ocean. So the rebeaching of plastic is actually also a sink, because this is plastic that's been traveling across oceanic currents like Laura and Nikolai Maximenko's group. They've been studying this. So I was with Nikolai for 2 years working in his lab, and that's basically his topic, is how plastic circulates in the ocean. And Laura was also in the lab, so she got interested in the topic and came to James Campbell as well. So well, the sea ice. So the sea ice is also a thing. So you get plastic trapped in polar regions, and this is hard to quantify as well. And then you have the atmosphere. So for some of you in atmospheric sciences, you have plastic that can resuspend into the atmosphere, and it can be used maybe as a cloud condensation nuclei. It can be transported and eventually fall with density, but a lot of it is actually floating in the atmosphere. And this is, for example, synthetic microfibers. So when your clothes are shedding synthetic microfibers, when you wear your let's say, polyester shirt, then these fibers, they are so small, then they will be very easily transported in the atmosphere. So these are all things, and there's more and more study looking basically at these things since 10 years, I would say. And it's very interesting, because in the end, we really want to find the global mass budget for plastic. So we want to close the loop and understand where is plastic trash going once it reaches the ocean. And of course, there are several plastic degradation factors in the environment. And here we are looking mostly as light. So the UV radiations, heat and fluctuating temperature. So depending where you are on the globe, if you're in the polar or in tropical region, then the temperature will have an effect on the fragmentation of the plastic. Then the moisture, chemical oxidation, biological activities, so microbial degradation, for example, Then you have the physical stress of the water on the plastic. You have the wave action and the salinity. So all of these environmental factors will have an effect on the degradation of the plastic and its fragmentation. And well, there are several degradation products also that gets released from the plastic once it fragments or even before it fragments. And so plastic is not inert and is known to release additives and other degradation products into the environment throughout its lifetime. And these chemicals, they vary. And once they are released, some can be toxic and have adverse effects for the environment and human health. And this common example about bisphenol A. So bisphenol A is used in the manufacture of many plastic products, and it leaks as plastics age. So we know that this has been used a lot with bottles for young babies. So we have to think, if we use plastic, we put the milk of a baby, for example, in the microwave, then you have all of these chemicals that will leak from the bottle to the liquid inside. So this is really something that, yeah, we should all be aware of, because it's not necessarily the plastic in itself that is negative for human health, but all of the different additives that are added to make plastic more durable or more flexible. They are very toxic for human health. So this is something to think of when you use plastic. Um, so most of the compounds reported today, they are additives and stabilizers that are added by the chemical industry, plastic industry, to the raw polymer. And these are very often a secret, like in terms of chemical formula. So it's really hard to get these the exact chemical formula of the compound that is being added to the virgin plastic, because the industry, they don't want to share this. So it's proprietary information. So what about hydrocarbons? So if you take, for example, polyethylene is basically carbon and hydrogen, C2H4 together. So if you have virgin material and you put this plastic in the environment, what will happen with these hydrocarbons? So this is a question that I haven't found many answers during my study, and this is actually my topic that I studied when I was at Seymour at the University of Hawaii with Sarah Ferron, Samuel Wilson, and I was in the lab of David Carl. And basically, we tried understanding better the degradation and the pathways of plastic once it's released in the environment. And I tried to give you a little topic on how we started the study. So I was not even in the lab yet, and Samuel and Sarah, they were looking at the biological production of methane from seawater. So their intention was to measure methane, quite low concentrations from seawater, and look at the concentrations according to different treatments. But they noticed that the concentrations were very high, and they could not understand. They were about 90% higher than what they expected. So they went back to their experimental design, and they realized that the bottles in which they were incubating seawater was responsible for most of the methane produced. So of course, after that, they quickly changed to quartz vials, but that was in itself a big discovery, which means then plastic emits methane, and methane is actually a gas that involved in climate change. So at that time, I was like, I really want to study this topic. So I changed completely my postdoc appointment. I asked my supervisor for many months to study this topic, and that's what I'm going to talk about today. So the first question that I tried answering was, which plastic type produces the most hydrocarbons? So we basically ran an experiment where we look at the 7 most common used types of plastic, which is polycarbonate, acrylic, polypropylene, then PET, like the plastic bottles, polystyrene, HDPE, and LDPE. We put them in quartz vials, and we expose them to natural solar light in Hawaii. And after 7 days, we measured, and we had our controls. So we had our controls for the cap, and then also dark treatment, just to see if the plastic would produce at the same temperature, but under dark condition. And then we were analyzing it with a GC for first methane and ethylene. And what we saw basically is that all of these compounds, whenever it's exposed to light, for methane and ethylene would produce these greenhouse gas. And some of them would even produce during nighttime. And the low density polyethylene was the type of polymer that would produce the most gases for both, for CH4 and C2H4. So what is low density polyethylene? So it's basically a plastic that's number 4 for the recycling facilities. And it's a plastic that is very highly used, the single-use plastic items for bottles or bags. And sadly, it's also the most used produced plastic polymers in the world, and its density is also lower than seawater, so it floats once it reaches the ocean, and it's expected to increase in the next decades. The global demand for polyethylene resins is rising 4% per year. So on top of producing the highest rate of gases, these are all the negative effects and the projection for this plastic in the future. So I decided to keep on studying LDPE. And one of the questions we asked was, does the concentration of the hydrocarbon gases keep on increasing with time? So what we did, we basically put pellets, virgin LDPE in quartz vials, and we looked at the concentrations of these pellets over time. And you can see here that we had our experiment for 220 days, and with time, it just kept on increasing. So we were wondering, like, is it the same for also the age LDPE? So we went on a mission in the Pacific, and then we used a manta trawl, as you can see here, and we basically scooped the surface of the ocean, and we collected plastic. Using Raman spectroscopy, we looked at the plastic. So the blue line here is the spectra for the virgin plastic, and the red line is the age one. So we found a match. We found age LDPE, and then we did a similar experiment where we took the age LDPE, we put it in quartz vials, and we looked at its concentration, production rate of gases over time. And as you can see, it also increased. So the release of greenhouse gases from virgin and aged plastic over time, these are the conclusion that we could quickly see, is that the polymers continue to emit gases to the environment, and this for an undetermined period of time. And we ran this experiment for over a year, and it just kept on increasing. And we expected it to be due to photodegradation of the plastic that will cause a surface layer marked with fractures, micro cracks, and pits. So plastic, as it's exposed to UV light, it will start like losing a little bit its property at the surface of the plastic. So you'll start having some small cracks and some small pits. And you can see this if you leave some plastic items outside. With time, it will start not being as soft as before. It will change color, and even if it's not fragmented into hundreds of pieces, as a one piece item, it still starts to create these small fractures until it breaks. And to confirm, we went to the biological electron microscope facility, and we looked at a plastic under an SEM, and we could really see that plastic, even though it looks like a very flat and soft surface, you have the creation of these cracks and microfractures. So on all of the plastic that we looked at, we could clearly see that the surface area is increasing. So another question we had, does the concentration of the hydrocarbon gases keep the same production rate when fragmentation occurs? So for example, you have one bottle and then it fragments into smaller and smaller pieces in the environment, like these fragmented piece of plastic. For the same amount of plastic, will we see a difference in production rate of gases? So when it becomes even smaller, like the microplastic you see here. So what we did, we basically looked at, we basically looked at LDPE in powder form. We look at 1 gram, and then we take the same LDPE, but in pellet form. And this was super interesting because we noticed that for the powder form, we have about 488 times more methane produced than for the pellet form, which is really worrying because we all know that plastic, once it's in the environment, it starts fragmenting and the surface area of the bottle increases. And I put this little scheme together where we look at one bottle and that butter starts slowly like degrading, changing its shape until it fragments. But for the same way, you get always more and more gases for all of the gases that we measured. Of course, I'm an oceanographer, so I started studying these experiments with plastic submerged in water, but I wanted to know if the data were similar when instead of taking the plastic, putting it in water in a quartz vials, we put it in the air. So we looked at the same plastic submerged in water and the plastic exposed to air directly. And this is when it got a little scary because we realized that there was about 3 times more methane produced when plastic is exposed to air rather than submerged in water. And 76 times more ethylene was being produced in air compared to submerged in water. So C2H4, ethylene is also a greenhouse gas, and so is also ethane and propylene that we measure. So all of these gases will be produced in a higher rate when plastic was basically found in air rather than in water. And then you think of this, like you see all of this plastic. This is Camilo Beach. It's basically on the island of Hawaii, big island. It's the most polluted beach that we have. And all of this plastic traveled through the oceanic currents. But then once it beach at Camilo, it will stay there for a very, very long time unless it gets removed by volunteers and cleanup organizations. So this plastic will be emitting more greenhouse gases than any plastic that is found submerged in water. But it's not it. We think always in terms of plastic pollution, but then all of the plastic that is in your backyard, your swimming pool, your car, greenhouses, landfills, all of these items, they basically emit a lot of greenhouse gases since they are all exposed to UV light. So this is something that we should always think of. And it's sad because it means that these two major issues, environmental issues in the world, which is climate change and plastic pollution, they are linked through this process. Then this is mostly due to UV light. And here, this is more of a summary slide because I just presented most of the work related to plastic that is basically exposed to UV light. So we know that solar radiation does enhance the degradation processes, but it's not the only factor. So we looked also at the surface area where we look at the differences between different types, like the powder I said and the pellets, but we look at different shapes and sizes as well. And we could see that surface area plays a major role. Then we did this one, air versus water. Then we also look at the production of these gases over night time. So once you have basically your phone case that is plastic exposed to UV light, and then you bring it back home, even if it's blocked from UV, it will keep on producing these gases at a lower rate, but still it will continue producing the gases in itself. Then the water surrounding the plastic pieces will also be emitting these gases. So probably because they are nano and pico particles, but once the water touches plastic exposed to UV, then it keeps on producing these gases over time. And finally, temperature. So we also ran some experiments where we look at the effect of temperature over time on plastic degradation, fragmentation, and the emissions of greenhouse gases. And of course, it has an effect. So it will, in the tropics compared to polar regions, more and more of these gases will be produced. So there's more to do, more work and more phenomena to study about this. And that's why I wanted to summarize all of this to get some motivation going. Unfortunately, I'm not working specifically on these questions at the moment, but there's really one question that interests me. And so again, I wanted to emphasize the fact that given the outgoing rate at which plastic is being produced, used, and disposed on land, and the future trend in mismanaged plastic waste ending up in marine system, it means that the amount of plastic exposed to the environment will likely increase with time, and so too will the amount of greenhouse gases emitted from polymers. So if we don't remove all of this plastic that is currently in the environment and remove it from UV light, then it will fragment and produce more and more of these gases. And yeah, this is the fragmentation and the effect of photodegradation over time. But so far, we don't have a good idea of how much plastic is currently exposed to UV light. So, and this is a pending question still today, because to answer the question, what is the contribution of plastic to the methane budget, we need to have better numbers of how much plastic is exposed to UV light. For the ocean, there are many scientists that's been studying the concentration of plastic floating at the surface of the ocean. But for terrestrial land, and we just said, and this is more important, the contribution is greater than in seawater. We have very little idea of how much plastic is currently exposed to UV light in terrestrial environments. So, and the world is busy. I mean, we look at the ocean, 70, a little bit more than 70% of the surface of the globe, but when we look at the continents and terrestrial environments, we know that there's a lot more plastic there. And this is a very important question to answer. How much plastic is in the environment? What's the surface area? What's the type of polymer? And this will help us answering the question, what is the contribution of plastic to climate change? And at the moment, we can only rely on satellites to help us detecting plastic. But knowing that a lot of the plastic, the size fraction of this plastic in the environment is really small, then it's really a big challenge. And there are several projects through the NASA, even the European Space Agency, that are trying to build different types of satellites to detect plastic from space. But it's a huge challenge because yes, we can probably see from up there a fishing ghost net that is gigantic because it's just possible to see it, but then when it comes to small fragments of plastic, it's a little harder to detect. So we really count on the new technology to help us answering this question. So that was my last slide, and I'm happy to answer any questions that you may have.
Thank you, Sarah. That was amazing, a very good talk. We don't have any questions yet, so si tienen preguntas pueden ponerlas en el chat y también vamos a leer las preguntas de YouTube. Okay, in the meantime, I have a question. So what are the current plans for capturing plastic or solving? Is there like yeah, what are the strategies?
It's a good question, and I wish I would have all of the answers to this one, but we have to think in terms of, so there's a lot of plastic that's been discarded into the environment since the 1950s, and it's still, as we speak, being discarded. And the only way to help with this issue is to remove the plastic from the ocean, from the environment. It can either be the ocean cleanup, removing it from the North Pacific garbage patch, or beach cleanup organization, removing it like permanently so it doesn't go back to the ocean and it doesn't keep on fragmenting into smaller and smaller pieces. So all of this plastic, we need to remove it. And yeah, beach cleanup organizations around the world are working on this issue. There are thousands and thousands of them every day removing plastic. So it's a big challenge. It's very little funded. It's not an easy issue to fix, but there's no other way around it. Like we cannot do anything else than removing it and picking it up. So that's for the plastic from the past and the present. But then you set a projection and how much plastic is expected to be discarded in the environment up to 2050. And for this one, the only way to reduce this curve is basically to find better materials, to use less plastic. And I truly believe that one of the best solutions at the moment will be to completely ban single-use plastic items. So these are about 40% of the total production of plastic. And single-use plastic items are so easy to replace. You can have like a bottle instead of a plastic bottle. You can have a bottle that will last for a very long time. An hydro flask can last for more than 10 years, I would say. So you can use this. You can use natural straw, natural materials such as bamboo or even metal. It's easy to clean. You can use your cloth bag to go to the grocery grocery store. So for the single-use plastic items, there are so many easy solutions. Then I think we need our policy and lawmakers to really stand for this and be like, okay, we're going to ban this. It's going to reduce the pollution by a lot, because all of these plastic, they are easy. They are used for a few minutes and they end up in the environment very easily compared to other heavier plastic that are not used in such a high concentration. So yeah, I hope one day this will happen, and we'll reduce our plastic waste by a lot if we do this.
Thank you.
You're welcome.
Okay, we have a question in the chat. How much contamination to the atmosphere implies the Pacific Ocean garbage patch? From Martin Saxon.
Oh wow, good question. I see atmospheric scientists answering this. So the North Pacific garbage patch, so there are 5 gyres in the world, and just to give a little bit of context, the North Pacific garbage patch is the closest to Hawaii, and we get a lot of the debris from there. And it's the most polluted like gyre in the world. Of course, you have a lot of floating debris there that fragments into smaller and smaller pieces. But I will say that the contamination to the atmosphere, the greater amount of contamination to the atmosphere might not be like over the ocean. It's most likely probably over terrestrial environments. And the reason is we always look at the ocean, but the landfills that you have and the fact that it degrades not submerged in water but directly exposed to air, the degradation processes are much faster. And I would think that landfills might be contributing a lot more to atmospheric deposition. But most of the time when you have plastic going in the atmosphere, it's because the density of the plastic is really, really small. The particles are very small and they can easily be picked up by the wind and be resuspended and then be kept in patches where they will stay in the atmosphere. Some of them might be going down, but yeah, for the measurements that we make, most of these particles will be microscopic particles, and you have a lot of synthetic microfibers. So all of the fibers that get detached from your synthetic clothes, when you wear them, they will go straight into the atmosphere. And depending on the currents in the wind, they can remain for a long time in the atmosphere. And they can also be resuspended later on, and they can bring some bacteria also in the atmosphere. So it's a very interesting process. I only studied microfibers, the synthetic ones in the atmosphere. I haven't looked at microplastic per se, but I know that there are publications looking into this. Sorry, Martin, I didn't answer quite your question, but yeah, nobody has studied the resuspension of plastic over the North Pacific garbage patch yet. It's a tough one. I guess we would need a boat, and I mean it's quite secluded, but yeah, I think it will be super interesting. I'm all about getting more knowledge on the topic for sure.
Thank you. We have another question from Carolina. Do bioplastic produce the same amount of hydrocarbon gases?
Yeah, that's a good question. So I haven't studied per se bioplastic, but I spent 2.5 years at Scripps Institution of Oceanography looking at the degradation of bioplastic over time. So I looked at different types of materials from polyester, polypropylene to bioplastic and cotton and natural materials. And what we noticed, it was basically that bioplastic, very similar to polyester. So polyester is the equivalent of a PET, a plastic bottle. So it's really synthetic, 100% synthetic compound. The bioplastic one that was PLA, polylactic acid, looked exactly the same as polyester after more than 1 year, meaning that when you take this bioplastic, you put it in the environment, you cannot expect it to biodegrade. And it's sad because there's a lot of the marketing strategies around us that are promoting the use of bioplastic and biodegradable materials. But the truth is that they never mention, but we need very high temperature and very high pressure for these compounds to degrade. So if you put them in the ocean, and I did the study for almost 2 years, they look exactly the same as plastic after 2 years, while cotton and wood-based cellulose, so it's similar to cotton, it's made out of cellulose, they degraded and fragmented in 30 days. So I thought PLA, the bioplastic, will use the same, like we will follow more or less the same trend, but no, they look as clean as it could get after more than 2 years. And I know another study about bioplastic from the University of Plymouth. They use bioplastic bags to go to the grocery. They put it for 3 years in water, and after 3 years, they could still hold a grocery load of 6 kilograms. So I was like, wow, this is crazy. So it's really greenwashing, and it's sad because sometimes consumers will think that they are doing a good thing by using bioplastic, but not really. In the end, you need very like powerful facilities that are probably not in your backyard to get it degraded. So it's not the solution yet.
Thank you. So we have another one. Do you want to read it, or should I read it for you?
Yeah,
So
the
that everyone.
production. Yeah, no, I can read it. The production from Carla Setter. The production of methane could be due to an incomplete reaction in the production of ethylene, which will be a problem for PET containers in addition to the environmental problem. So yeah, when we study actually the production of methane from polyethylene, so polyethylene is C2H4. It's an hydrocarbon. It's actually CH2, but it's not stable under our atmospheric pressure. So C2H4, and then you add some oxygen molecule or water vapor to it, and then you have the reorganization of the molecules that gives CH4. So actually, I mean, it was a discovery, but it's not rocket science because it can be expected to be produced. It just nobody really looked into this, and the plastic community knew, like the plastic manufacturer, I think they knew. They never wanted to share any information with me, but it's kind of impossible that they never heard of it. So I would suspect, and they always told me that they are not interested in discussing with me. So I suspect them to know because it's a simple stoichiometry like formula to look into. So we have ethylene. So ethylene is C2H4. So when you put LDPE, that is C2H4, under sunlight, you get C2H4 as a product as well in the gas form. You get also C2H6, you get C3H6. So you have a reorganization of these molecules. And I measured them before, and I measured CO2 as well that will be produced. But I suspect there are probably thousands of gases that are being produced. It's just we don't measure all of the byproducts, which is sad because probably a lot of these gases that are being emitted are part of the sinks to the missing plastic, and also they have an impact on the atmosphere. Then if we look into PET, PET is a little bit more complex in terms of chemical molecules, but yeah, it's also a polyethylene one with terephthalate at the end. So yeah, absolutely, you'll get C2H4 produced as well from PET. So when you try basically to recycle these bottles, then you definitely have all types of gases that are being produced. So I hope I answered your question, Carla.
Thank you. So I don't see any other question. Okay, here's another question in the YouTube channel from Marisol. Do you think that plastic eating bacteria can help us reduce the concentration of plastic in the ocean?
Yeah, that's a very trendy question. And I wish I could say yes to this, but the truth is that the amount of plastic that we have today in the environment is gigantic. And if we would need to have like bacteria, there's a PETase that's been found, so a bacteria that could help degrading and using plastic as a source of nutrients. And there's a worm, for example, but if you would want, and these are very slow processes, so if you would want to have bacteria to degrade all of the plastic we have, it would be a concentration so high that the entire ecosystem would be completely like traumatized. So I wish this could be a solution. Maybe this could be done in landfills, but at the rate that we discard plastic in the ocean today, I don't think this is the solution. The solution is really to stop plastic from the source itself.
Thank you. So I'm going to ask one more. Okay, yeah.
No,
Laura?
I want to ask you something. Like you say that bioplastic is not the magic solution or is not a great solution. I was wondering if the recycling of the plastic, like for making shoes and clothes, is a good way to mitigate the problem, or is also about maybe you are trying to use that plastic, but at the same time maybe you are emitting more gases in the process, or maybe if you know something about the production of clothes and shoes.
Yeah, this is a very good question. And just 2 weeks ago, I got a publication that is now online, where we are basically looking at the degradation of synthetic materials over time. And to answer your question, for example, if you have like hundreds of thousands of PET plastic bottles and you want to use them, to repurpose them and create a material, then don't use this to make a shirt, because if you use it to make a shirt, when you wash your clothes, you release so much microfibers. And if they are synthetic, it means that they go straight into the ocean. And I have some numbers, like 6 kilograms of polyester. If you wash it in your washing machine, you get about 750,000 synthetic microfibers that are released into the waterways. And a microfiber is about 1/5 the diameter of a human hair. So it's so small, and you cannot put a filter to stop them. Otherwise, the flow of the water will be too slow. So they basically go all the way into your wastewater and ends up some of it in the ocean. So if you want to, and I'm all about repurposing plastic, with the amount we find in Hawaii on this picture, for example, if you pick it up, then you send it straight to here it's net to energy, like you can make electricity with this, but it took so much energy to produce it. Then if you want to repurpose it, you have to do it in a very smart way. And for me, I studied synthetic microfibers, so I would not make like clothes out of marine debris. And I know it's very trendy, and a lot of brands are trying to sell the board shorts made out of PET bottles, leggings, but it's hard, because then you just end up putting them back in the environment after. I mean, it's a lot of effort to organize beach cleanups and picking up the trash. So you have to think, what will I do with it? So first, it's not exposed to UV light, so it doesn't emit greenhouse gases. And second, it doesn't fragment and go back into the environment. And I would say that, and I have one here, I could pick it up. There are these bifusion blocks to make buildings, and then you can cover these blocks made out of plastic waste for like a house, for example. So I think if you use this for building and for industry, that might be a good solution, because it's not exposed to UV and it doesn't fragment, and it's not released in the environment.
Thank you.
Okay, thank you. That's been great. Since we have a little bit more time before 6, I want to ask one more question myself. So you mentioned temperature and how temperature may affect how much these plastics emit. How much is that? Because I think you said that in the end, or if it said it, I missed it, but like per degree of warming, for example, how much more will this plastic be emitting? Because it sounds like a possible like feedback effect or something.
Yeah, and I think with El Nino, La Nina, I mean, you have all these fluctuations of temperature, and I think this will affect greatly like the degradation rate of plastic and emissions of greenhouse gases. But I looked only at 3 temperature. I looked at 0 Celsius. I looked at 20 and 40, just to have an idea. But I think I would need to probably run more experiments to get a formula and see if it's linear or not. I don't think it's linear. I think it's probably exponential until it melts. But yeah, it's a tough question. You take synthetic turf, for example. Synthetic turf, that's fake grass to play football. it's so popular nowadays. And the temperature of synthetic turf can go as high as 89 Celsius. So it's really hot. Like you can barely put your feet on there. And the surface area is super huge. So with the temperature in the surface area, you have a gigantic amount of gases that are being emitted straight to the atmosphere. But yeah, I know it's important temperature. I haven't studied it enough to give a formula, but I would think that it's probably exponential.
Thank you. Okay, so if there's no more questions, I'm gonna thank Sarah again for her great talk. We have a lot of comments here thanking you for your very interesting presentation. So thanks
Very
again.
welcome. That was a pleasure. Muchas
And
gracias.
gracias a vos.